Welcome to the deep dive. Today, we're plunging into a field that, well, lets us peer inside the very hearts of stars, and not with a telescope, not visually, but by actually listening to their whispers. It's quite amazing. We're talking about asteroseismology, the science of stellar oscillations. We've got some really fascinating source material that honestly promises a bit of a shortcut to understanding how we use these vibrations, these stellar shakes, to figure out really basic things about stars, like their masses, their radii, their luminosities, the fundamentals. And here's where it gets really interesting today. We're going to focus on a special area. It's called gravito-inertial asteroseismology, I guess. So while asteroseismology is broad, this specific type looks at gravity modes. Think of them as waves deep inside the star, driven mostly by gravity and the star's spin. These modes tell us about the core, the internal rotation, its deep stuff. And we'll explore how the incredible Gaia mission, which wasn't even built for this, is making a huge impact, almost accidentally. It's kind of like a cosmic ultrasound, really, seeing inside these spinning stars.
That's a great analogy. And yeah, the mission for this deep dive is exactly that. Understand what the oscillations tell us, but also how we study them, especially these gravity modes, the G modes, in rotating stars. And crucially, what new things Gaia is showing us about their insides. What's really fascinating, I think, is how data from Gaia, which can seem sparse for this purpose, still gives us so much value.
Yeah.
Especially when it's carefully checked against other missions, like Kepler. That validation is key.
Okay, right. So let's unpack the history a bit first. How did we get here? Because before the 1950s, scientists mostly thought all the variability we saw in stars was just radial pulsations.
Yeah.
Like you said earlier, imagine a star just puffing up and shrinking down like a giant lung or a balloon, all parts the same distance from the center moving together perfectly in sync. And that worked pretty well for stars like RR Lyrae and the classical Cepheids.
Right, the well-known ones. But that simple picture couldn't last, could it? What started to poke holes in that? What did they find that just didn't fit?
Yeah, exactly. Things got complicated. They started finding higher frequency variations, periods that just didn't line up with simple radial pulsations. And then the real breakthrough, I think, was in 1951. There was a scientist, Ledoux.
Ledoux, yes.
He showed that these non-radial oscillations, so not just in and out, but more complex wiggles in a rotating star, could explain what was going on with a specific bright star, ACMA. It had this really complex variability, different periods close together, weird phase shifts between how its spectral lines broadened and its measured velocity.
And Ledoux's non-radial model explained it.
It did. It showed how these other kinds of oscillations, driven partly by rotation, could produce that complexity. It was a total game changer.
Absolutely. And connecting that to the bigger picture, later studies showed these non-radial oscillations weren't just some weird thing in one star. They're everywhere. All across the HR diagram, you find them in Cepheids, Delta Scoot stars, even way down to white dwarfs, and of course in our own sun. They're fundamental.
That's right. And listeners might have heard of this next part. 1962, Leighton and his colleagues discovered the 5-minute solar oscillations. That discovery basically launched the whole field of helioseismology.
Studying our sun's interior using its vibrations.
Exactly. Using those non-radial pulsations to map out the sun's insides in incredible detail.
And then building on that, in 1971, Osaki showed how these non-radial pulsations don't just make the star wobble, they also directly affect the light we see. They cause periodic changes in the shapes of spectral lines, their width, their depth, their symmetry, which is absolutely crucial because that's often how we actually detect and measure these oscillations from Earth. We see it in the starlight spectrum.
Okay, so we've established stars don't just breathe. They wiggle and twist in complex ways, non-radial pulsations. How do scientists actually describe these complex movements? You can't just say it wiggles, right?
No, you need a precise language. And that language is spherical harmonics. It's a mathematical way to describe vibrations on a sphere. These pulsations are characterized by their frequency, how fast they happen, and then 3 key numbers, sort of like quantum numbers. Okay. There's the radial order M. That tells you how many crossing points, or nodes, the wave has between the star's center and its surface, radially. Then the azimuthal order, 2 times some, gives you the number of node lines running longitude-wise around the star.
Like lines of longitude on Earth.
Exactly like that. And finally, the non-radial degree, M. That tells you the total number of nodal lines on the surface, including ones parallel to the equator.
Wow. So it's like a 3D map of the star's internal vibrations. Each mode has its own unique NLM signature.
Precisely. It's a blueprint for that specific wiggle. That's how we decode the signals and figure out what's happening inside. It's a complex work, teasing apart all these different modes from the light we observe.
Right. Okay, so that sets the stage. We know stars vibrate complexly, and we have ways to describe it. Now, let's jump forward to today. And Gaia, this mission that was primarily about mapping star positions and movements.
Astrometry, yeah.
How on earth did it become such a big player in asteroseismology, the study of stellar interiors?
It's a fantastic story, really. And a key piece of this comes from a recent study Arts and colleagues in 2023. They looked at an absolutely mind-blowing number of stars, classified by Gaia over 15,000 as gravity mode pulsators, G-mode pulsators.
15,000, that's huge.
It is. And what's impressive is their careful approach. They didn't just take Gaia's classifications at face value. First, they independently checked if Gaia got the classification right, are these really G-mode variables. Then, for stars that both Gaia and Kepler observed, they compared the data. Does Gaia's view match Kepler's more detailed look?
Kepler being a mission designed for finding these kinds of variations.
Exactly. So a crucial cross-check. And only after validating Gaia's metrics this way did they apply them to study the full, massive Gaia sample. That step-by-step validation gives you confidence in the results from that huge data set.
Makes sense. And which specific types of stars were they focusing on within that massive sample?
They zeroed in on two main types: slowly pulsating B stars, SPB stars, and Gamma Doradus stars, or Gamma Dor stars.
Okay.
These are main sequence stars still burning hydrogen in their cores. They range from about 1.3 up to maybe 9 times the mass of our sun.
And they have convective cores, right, churning centers.
That's right, and that structure makes them ideal labs for studying these G-modes. Their complex oscillations are really sensitive probes of what's happening deep inside, especially the internal rotation.
But wasn't there a complication? I remember reading that many of these Gaia G-mode pulsators were found, well, outside the places where theories predicted they should be pulsating.
Yes, that's a really important point, and it came up in earlier work too. They appeared outside the standard instability strips on the HR diagram.
So outside the zones where our models say stars of that temperature and luminosity should be unstable to pulsations.
Precisely. And finding them there is puzzling. It suggests maybe our understanding is incomplete. The study suggests a few possibilities. Maybe Gaia's temperature measurements have some inaccuracies for these stars.
Okay.
Or maybe the stars are rotating so fast it changes where they pulsate. Or perhaps the physics in our models, like how opaque the star is to radiation deep inside due to heavy elements, isn't quite right.
Or even being in a binary system could be driving the pulsation.
Exactly. It could be a mix of these things. But the key takeaway is that these outliers are pushing the boundaries. They're telling us where our models need improvement. It's exciting, in a way.
It really forces a rethink. So, okay, they validated Gaia against Kepler. How well did Gaia actually perform? How did its measurements stack up?
They compared Gaia's derived properties, luminosity, temperature, surface gravity for these pulsators, against a well-studied set of 63 known G-mode pulsators. These had data from Kepler plus detailed follow-up spectroscopy.
A smaller but deeply understood comparison group.
Right. And for the Gamma Dor stars, the agreement was remarkably good. The distributions Gaia found for effective temperature, luminosity, and radii matched the Kepler spectroscopy sample extremely well.
Wow.
Even though Gaia's sample was huge, over 11,000 Gamma Dors compared to just 37 in the Kepler comparison group.
That's impressive validation.
It really is. Gaia's gravity measurements were a little lower than the asteroseismic ones, but overall, the agreement, especially given the sample size difference, is a powerful testament to Gaia's capabilities here.
Okay, what about the other group, the SPB stars?
For the SPBs, it was a bit trickier. Gaia's sample tended to pick up the cooler, less massive examples of SPB stars compared to the Kepler sample.
So not a perfect overlap in the types of SPBs being compared.
Correct. Also, Gaia's observations are spread out over time. Its temporal coverage isn't as dense as Kepler's. This limits how precisely you can pin down the main pulsation frequency from Gaia data alone.
Right, Kepler stared intensely at stars for long periods. Gaia scans the sky.
Exactly. But even with that limitation, the dominant frequencies Gaia did find were broadly consistent with what Kepler saw. It seems Gaia DR3 can reliably detect these G-mode frequencies as long as their brightness variation, their amplitude, is bigger than about 4 millimagnitudes.
4/1000th of a magnitude. That's pretty faint.
It is. It means Gaia is sensitive enough to pick up even these relatively subtle, deep-seated G-mode whispers, which is fantastic for probing interiors.
So you can detect the frequencies, but you mentioned earlier identifying the actual the NLM quantum numbers. How do we do that, especially if the star's spinning fast and smearing things out?
That's where spectroscopy comes in again, ideally high-resolution spectra taken multiple times. These G-modes cause bumps and wiggles to move across the star's surface, and this changes the shape of the spectral lines we observe.
Ah, not just the star's overall brightness changing, but the details within the spectrum.
Exactly. The line profiles vary. These variations can be quite significant, maybe changes of several kilometers per second or even tens of kilometers per second in the apparent velocities across the line shape. Disentangling these variations from the general broadening caused by the star's rotation is challenging. It requires good data.
But if you can disentangle it,
Then analyzing how the line profiles change over time is a powerful way to identify the specific spherical wave numbers, the L and M values of the strongest oscillation modes.
and did the art study find anything in the Gaia data itself that helps with this, beyond just detecting the frequency?
Yes, they did. They found that a specific measurement from Gaia's radial velocity spectrometer, the RVS instrument,
Okay.
called Vizinus, which is meant to estimate the line broadening due to rotation, actually does a pretty good job of reflecting the time-independent part of the broadening. This basically confirms that, yes, surface rotation is the main thing broadening the lines overall in these stars, as expected.
So Gaia can give us a decent estimate of the rotation's effect.
It seems so. And interestingly, they also found that the dominant G-mode frequency itself was a good predictor of another Gaia parameter, V broad, which measures the overall line width and also how much that width varies, V broadstev.
So the pulsation frequency is linked to the measured line width and its variability. That's fascinating. It suggests Gaia's spectra hold clues about the pulsations beyond just the overall brightness changes.
It really does. It ties the pulsations directly to observable spectral features in the Gaia data itself.
Okay, so let's pull back and look at the big picture here. What does all this mean for you, for the listener, for the whole field of asteroseismology? It sounds like Gaia, even though it wasn't designed for this, is turning out to be incredibly useful, a bit of an accidental hero.
Accidental hero is a great way to put it. It's making huge, genuinely unexpected contributions. And if you think about the big picture, Gaia is delivering on multiple fronts for astroseismology. It gives us incredibly precise distances, trigonometric parallaxes, which are absolutely crucial for testing and calibrating our astroseismic models of stars. You need to know how far away a star is to know its true luminosity.
Right, distance is fundamental.
Then, as we've discussed, it's providing variability classifications for vast numbers of stars, identifying likely pulsators on an unprecedented scale. It places these stars very precisely on the HR diagram thanks to accurate brightness and temperature data.
Which helps test the instability strip predictions.
Exactly. It's discovering huge numbers of new pulsators and even helping, as we saw, with identifying their oscillation modes. And finally, through its RVS spectra, it's giving us these amazing insights into line broadening, rotation, pulsations, maybe other effects too. It's a goldmine of data for anyone wanting to understand what goes on inside stars.
So we've really seen today how Gaia, this mission that was mostly about mapping where stars are, has become this incredible tool for understanding what stars do internally. It's helping us hear the music of the stars, their internal vibrations. And it's just a powerful reminder, isn't it, that sometimes the biggest breakthroughs come from looking at data in new ways or from tools that were built for something else entirely, unexpected discoveries.
Absolutely. And it really makes you think, doesn't it? It raises this important question. If Gaia, which wasn't optimized for astroseismology, can tell us this much, what fundamental new secrets could we unlock when future missions combine Gaia-like astrometry with even more powerful, dedicated astroseismic instruments? Imagine what we could learn by listening even more closely with even better tools. What hidden physics inside stars is just waiting to be uncovered. When you think about everything we've discussed, what's the one thing that really stands out to you from this deep dive?